In this video, we will talk about how stoichiometry can be used to determine how much metal has been reduced in an electrolytic cell. When we do cell stoichiometry with electrolytic cell, we can determine the mass of the substance that can be reduced or produced at the electrode if we know the quantity of electricity that passes through our electrical system. So for example, when we coat zinc onto a steel pipe to what's called galvanize it to prevent it from rusting, 2 moles of electrons must be gained for every 1 mole of zinc. Because zinc ions, being +2 charge, requires 2 moles of electrons to produce solid zinc. So therefore, if we can calculate how many moles of electrons are transferred in our reaction, we can determine the number of moles and the mass of zinc that is produced in our reaction. So if we look at our table of half reactions, we can once again determine the reduction half reaction for zinc. And for every 1 mole of zinc, the invisible one here, we need 2 moles of electron. How can we determine how many moles of electron is transferred in a reaction? Well, unfortunately, there is no meter or an instrument to directly count or measure the number of electrons because the electrons are too small. However, we can use the ammeter function to determine the current. We can use the current to then indirectly determine number of electrons. Now, before we talk stoichiometry in chemistry, we need to do some physics. And the physics formula we need to use is Q equals I times T, where Q is the charge, the quantity of charge, that's why it's used the letter Q, capital Q, and Q is measured in coulombs, and the symbol for coulombs is a capital C. Electric current is I, capital I. It is measured in amps, or capital A. And 1 amp is equal to 1 coulomb per second. And time, little t, is time measured in seconds. Using this formula, we can then determine the quantity of charge that is transferred in a reaction if we know the current that it was going through, as well as the time the current was applied for. And 1 coulomb is the quantity of charge transferred by 1 amp during 1 second of time. So again, 1 amp equals 1 coulomb per 1 second. So 1 coulomb equals 1 amp multiplied by 1 second. Now, the first chemist to study the quantity of charge and electron was Michael Faraday, and he did this work in the 1830s. And what he found that 9.65 times 10 to the 4 coulomb of charge is equivalent to 1 mole of electron. So now we have this, what is called our Faraday constant. The Faraday constant, or capital F, is 9.65 times 10 to the 4 coulombs per mole of electron. We can use this constant as a conversion value between the quantity of charge that we can measure through an ammeter as to compare it to the number of moles of electrons. So again, the Faraday constant can be used as a conversion factor to convert electric charge that we can measure to the moles of electron. And the way we do this is using this formula. Moles of electron equals the quantity of charge, the coulombs, divided by Faraday's constant. So N equals Q divided by F. Now before, on the previous slide, we said Q equals current multiplied by time. Q equals I times T. So we can substitute this into our equation here to get another new equation. N equals the current multiplied by the time in seconds divided by Faraday constant. This formula will give us the moles of electrons if we know the current and the amount of time the current is applied for, and if we divide the product of those two values divided by the Faraday's constant. Let's do a quick example to solidify our understanding. Here we're asked to find what amount of electrons is transferred in a cell that operates for 1.25 hours at a current of 0.150 amps. So here we list all our known variables. We know our current is 0.150 amps. Time is 1.25 hours, but we need to convert from hours into seconds, so we multiply by 3,600 seconds per hour equals 4,500 seconds. And the Faraday constant which we can look up in our data table, is 9.65 times 10 to the 4 coulombs. So using our equation, where the number of electrons, the moles of electrons, is the current multiplied by the time divided by Faraday's constant, we plug everything in here into this equation, and we do our math, and we find out that the moles of electrons is 6.99 times 10 to the minus 3 moles of electron. Now, when we do our stoichiometry, we often want to find the mass of element that is produced at the cathode. Now, because this is totally dependent on the number of electrons transferred, we need to know the half reaction, a balanced half reaction, so that we can get a stoichiometric ratio. Now, we can use our skills from other courses and other stoichiometric calculations to calculate the amount of metal that is formed at our cathode. The only new thing about cell stoichiometry is that we need to use Faraday's constant to convert a quantity of charge into moles of electrons. So let's look at an example where we have to use Faraday's constant to convert a quantity of charge into moles of electron, and then convert the moles of electron into mass of a metal. The question here is, what mass of copper is deposited at the cathode of a copper electrorefining cell? So again, this is a type of electrolytic cell, whereas current is pumped into the system so that the copper ion is reduced into copper metal at the cathode. First thing to do, as for any stoichiometric ratio, we look at a balanced reaction. Here, we only need to look at the balanced half reactions. Now it says copper is being deposited at the cathode, so at the cathode, we know it's a reduction equation. So we look up the reduction half reaction of copper 2 plus ion into solid copper. We can also write all the other information that we're given. We know it was on for 40 minutes. The current was 12 amps, and the molar mass of copper is 63.55 grams per mole. And lastly, Faraday's constant is given to us right there. The first thing we need to do is to convert our quantity of charge into moles of electron. But to find a quantity of charge, we need to use the formula Q equals IT, or we can use the formula, the number of moles of electron is I times T divided by F. We were told the current was 12 amps, or 12 coulombs per second. Time, it was 40 minutes, but then we convert the minutes into seconds by multiplying by 60, divided by F, Faraday's constant. Calculate that value, and we determine that we have 0.298 moles of electron pass through the cell during the 40 minutes. Now that we have the moles of electron that went through this half cell, we can use stoichiometry, the mole-to-mole ratio, to determine the number of moles of copper produced. So here we have 0.298 moles of electron times our stoichiometric ratio. Our stoich ratio here is our invisible 1 to 2, 1 to 2. And notice the moles of electrons are going to cancel out. In our stoichiometric ratio, 2 moles of electrons, electron has to be on the bottom, so that the moles of electrons cancel out, leaving you with 0.149 moles of copper. And the very last step, we need to convert the moles of copper, 0.149, into grams of copper, and we do that by multiplying them by the molar mass, 63.55 grams. So then we get, at the end of the day, 9.47 grams of copper should have been reduced at the cathode from copper ions into solid copper. So again, this is a stoichiometric question, and the only twist to it is that we have a current and a time, which will give us a quantity of electrons. We then need to use Faraday's constant to convert the quantity of electrons into moles of electron. And once we have moles of electron, we can do stoichiometry as we have done in the past.